Let's look at the example that Krysiak gave in your reading. In this example, a board of directors for a property, a piece of land, they're trying to determine what to do with it. And they have the option of leaving it undeveloped as it is, this is the status quo option, or developing it for different uses, for residential use, so building houses, for industrial use, allowing manufacturing plants to build in, recreational use, so developing it as a natural use area. Now, they did some research and determined average annual benefits from each of these different uses. This is mu here, our expected average, our expected mean benefits. Now, this is related relative to the status quo, these values, these numbers here. And sigma then is our standard deviation. This is the variance around our mean. You can see that all of our alternatives would be better than the status quo. We would be receiving 33% more benefits if we developed for recreational use, 66% more benefits on average if we developed for residential, and 100% more benefits if we developed this land for industrial use. So, which alternative do these numbers suggest that we take? The industrial, right? We should get the most benefits from the industrial use. This has the highest mean. If we were taking a deterministic approach, let me write that out. Deterministic approach, then we would go with the highest suggested value, the best. But this is not the whole story, right? We also need to look at the variance. And this is where a graphical representation really comes in handy. These are the normal distributions for each alternative. Our x value is our expected benefits. And I grabbed this picture straight from the reading, so I apologize for the pixelation here. The industrial option has the highest mean. Remember, the normal distribution is centered on the mean. The industrial option has the highest x value for the means. But the industrial option also has the largest spread. It's the squattiest of our normal distribution. And all of these curves represent 100% of the outcomes for each option. So if it's more squatty, that means that there's going to be more opportunity for low values and high values. It's got a larger variance. Let's magnify this graph. Let's take a closer look at the bottom left corner of the graph here. This is where this box is. We're going to zoom in and look at where the status quo falls within each of these normal distributions. I'm going to trace these lines with different colors. Hopefully you can see them a bit clearer. So our industrial use, that's the one that had the widest variance, goes way down here, whereas our residential curve goes something like this, and our recreational option, kind of a steeper curve here, drops down pretty quickly. Now the status quo line right here, this is the status quo. It represents our annual return. These are the benefits from the land in the current state. Now that we've magnified this part of the graph, can you tell which option has the least risk of harming the future generation? In other words, which of these alternatives has the smallest probability, or the least area under the graph, of returning less than the status quo? So which one of these areas from status quo to the end of the tail, which one of the curves has the least amount of area? Well, it looks to me like the option residential has the least amount of area, right? That would be just this area. It's probably a smaller area than recreational, and definitely a smaller area than under the curve for industrial. So by considering the mean and the variance, the residential option has the smallest probability of returning less than the status quo. So to summarize, with the mean-variance method, we define the risk of harming future generations as the probability of receiving less benefits than status quo, and we determine this risk as an area under the normal curve. The mean-variance method answers the question, which alternative option or plan of action has the least risk of harming future generations?